Welcome to my talk on my paper covering polygons is even harder. Some of you might have seen this figure here before. It's used as the logo of the Society for Computational Geometry and often also for the SOCIET conference. And it comes from an old paper by Joseph O'Rourke from the Allerton conference. And he studied the problem of covering a polygon with a minimum number of convex polygons. So here you can see part of the solution. We can use 8 rectangles to cover most of the polygon like this, but then we will have these regions here that are not covered, but those can be covered by adding this orange square. And the interesting thing to see is that this orange square, it cannot be obtained from extensions of the edges of the input polygon. So that shows that this solution is actually not so easy to get to. So to formalize the problem we are looking at, the minimum convex cover problem, we are given a polygon P and an integer K. And we want to know if there exists K convex polygons Q1 up to Qk, such that when we take the union of those, we get our input polygon P. And this problem was actually studied even earlier by Polygons in some papers, and he's from a more practical point of view, and he showed that it's an important problem in shape analysis and shape recognition, because if you compute the minimum convex cover of a shape, then it gives some important information. And here you can see 2 examples from an E and a Chinese character. And in this paper by Joseph O'Rourke, he proved that the problem is decidable, which is not at first obvious. So he proved that it's in this complexity class existential theory of the reals that I will get back to. So even before that, the problem of partitioning a polygon into a minimum number of convex polygons had also been studied. So there you don't allow these pieces to overlap, and therefore you might sometimes need more pieces. And here's an example. You need 3 convex pieces to if you want to partition into convex pieces, and you can do with 2 if you just want a cover, because they can overlap here in the middle. Then the convex cover problem was proven to be NP hard if there are holes in your polygon, and then later on also when there are not holes. And then in 2001 there was given a log n factor approximation, and the problem was shown to be hard to approximate. And then in 2011 the version where you want all your pieces to be triangles was also proven to be NP hard. Then a few years ago, we proved that another related problem, the art gallery problem, is complete for the existential theory of the reals. And the art gallery problem, that's actually just covering a polygon with a minimum number of star-shaped polygons. And then 2 years ago, we proved that many packing problems are also complete. For instance, given a set of polygons, decide if they can fit in a rectangle, as you can see an example of here. This complexity class existential theory of the reals, it lies somewhere in between P space and NP. And I will get back to how it's defined. And in this new paper, I prove that the minimum convex cover problem is also complete for the existential theory of the reals, also the triangle cover problem. And the reason I include these 2 papers here in the history is that I will use techniques from both of these papers to prove that. So you can define the complexity class from this problem, ETR, and the input is some variables here, x1 up to xn, and then a formula where these variables appear. And then you want to decide if this formula is true or not. That means whether you can choose real numbers so that you get a true expression. And the formula is written up with these symbols here. You have 0, 1, and you have your variables, and then you have equality and strict and weak inequalities. Then you have addition and multiplication, and you have logic operators and, or, and not, and parentheses. So with this, you can build all kinds of polynomial equalities and inequalities. And then you want to know if this system of polynomial equalities and inequalities, if you can satisfy it by choosing real values for your variables. You can then define the complexity class as all problems that reduce to this problem in polynomial time. And then you say that a problem is hard for the class if you also have a reduction in the other way, just as we could do with NP from the set problem. But it will be more convenient to reduce from a specialized type of these formulas. So I will reduce from a problem called range EGR_inf. So there we are again given real variables, and then together with each variable we have an interval that the variable has to be in, and then we also have a collection of formulas CJ. Each of them has one of these forms. It can either be an addition constraint like this, so we have the two of the variables should sum to a third one, or it's an inversion, so the product of two of the variables should be 1. And then these intervals here that the variables have to be in, they are all sub-intervals of the range from 1/2 to 2, and each of them is very small. So each of them has a length which is of the order of n to the minus c for any constant c. And in our paper on packing problems, we proved that this problem is actually also complete. So therefore, we can use it to reduce to other problems. The proof structure is that we first reduce range EGR_inf to a restricted type of minimum convex cover problems called MRCC. And then we reduce that to the general minimum convex cover problem. So in the restricted version, we have some special marked corners that we have to cover. And then we have some marked rectangles in the interior that we have to cover, but other things we don't need to cover. So we want to know if we can cover these things, the red corners and the blue rectangles, using a certain number of convex pieces. And then in order to reduce that problem to the general problem, we add some spikes so that covering these spikes, we can cover everything except those marked corners and marked rectangles. Yeah, so here you can see that we could cover these marked corners and rectangles using 3 pieces. And up here, we can then add some pieces covering these spikes so that we will cover everything else. And here I've only added some of the spikes to not make the figure messy. But the main work is to reduce the range EGR_inf to this restricted version of convex cover. So because we are reducing from this range EGR_inf, where we have real variables, we need to find a way to represent real variables geometrically. The overall design is similar to the one we used for the art gallery problem, where we have some base pockets down here where we represent variables, and then we have some gadgets up here that we can copy variables into, and then these gadgets, they will simulate the addition and inversion constraints that we have in our range EGR_inf instance. In our art gallery paper, we represented a variable by one guard that had to be placed on this guard segment And if it was standing at the left endpoint, it would represent the value 1/2, and the right endpoint is 2, and then we interpolate between those two values. And then by sliding it back and forth, it would see more or less on the other side of some corner here that is blocking visibility. Then here in the convex cover problem, we instead have one piece that will partially cover our variable segment here. And the more it covers down here, the less it can cover here on the other side of a corner, because it has to stay convex. In the art gallery paper, we could have one guard here that would see into multiple pockets here, and then we would have sort of multiple copies of the same variable. That was important because we can have the same variable appear in a lot of these constraints. But that's not possible in the minimum convex cover problem, because if you have a piece that covers something in a gadget here, then it cannot also cover something in another gadget, because it has to be a convex piece. But instead, we can make many copies of the same variable by having a piece as this green piece here that partially covers a lot of variable segments here. And then each of them will have their own piece that covers the rest. And then each of those pieces can then also cover something in a gadget. So that's sort of the main insight that makes this work. Then the general technique is that we can make these chains of inequalities. So we have a variable segment here, and the green piece will cover part of it. And then we have another one representing the same variable down here. So if it covers more up here, then it will cover less here. And then we have the pink piece here that has to cover the rest of that one. And then it can also cover something of the one up here. And the blue piece that will cover the rest, and then some of this. So doing it like this, we will actually have a dependency of how much the green piece covers of this variable segment here, and how much the blue covers of this one. So therefore, we can make these chains of inequalities between the values that we represent different places in our polygon, and that's the technique we will use to transport these values around in the polygon. And as you recall, we had the requirement that each interval is very small. It's n to the minus c for some constant that we can choose. And that corresponds to that we don't need the flexibility to represent all values on our variable segment. We have some small sub-interval on it that we should be able to represent. And because it's n to the minus c, we can think of it as basically just a point. So we need only some infinitesimal flexibility to rotate back and forth and represent different values. And that will make it much easier to make a construction that will work. And that's the reason why this is a good problem to reduce from. Okay, so the overall design of our polygon is that we have those base pockets down here. And the total width of them is proportional to capital N, which is the size of the range ETR-inf formula that we reduce from. And then we have our gadgets up here, and then the total height of those will again be proportional to our formula size. And the distance here will be proportional to the square of that size. Okay, and then the base pockets, they look like this. So we will have some large pieces here that can cover partially a lot of variable segments in each pocket. And then the remaining part of each segment then will be covered by what we call a propagation piece, with a very long skinny piece that can cover a little bit of that segment, and then stick into some gadget very far away up here, and then cover something up in that gadget also. So in each gadget, we will have to copy in 2 or 3 values. And the way we do it is that we have, for instance, 3 segments here that have to be covered by some propagation pieces. And then we also have 3 segments here in our gadget that we want to match with those 3. And then we make a corridor where we also have some marked rectangles that should be covered. And then they will be the pieces have to sort of cooperate in pairs to make this covered. And we do it so that it's not possible for any piece to cover something in that it's not supposed to do. We do that by finally adjusting these openings in the corridors, so that the pieces can only cover the things that we intend them to do, and therefore we can be sure that we cover the values correctly into the gadgets. The actual gadgets turn out to be quite complicated. So for instance, here is an addition gadget, and so here you can see we copy in 3 values to a variable segment here, here, and here. And then we have a special region here. You can see a close-up of it here. So we have a special green quadrilateral that we need to cover. And then we can prove that if the piece, this piece here that covers part of this segment, and the piece here that covers part of this segment, and the pink piece here that covers part of this one, if they together cover this green quadrilateral, then it's because the value represented here is at most the sum of the values represented here and here. And then again, we don't need to cover the entire quadrilateral because we have the restricted ranges. So we just have some infinitesimal quadrilateral here that we actually need to cover. And in order to make this work, I couldn't find another way than to make quite long chains of inequalities. So here you can see we copy from this one to this one, and then from this one to this one, and down here, and then finally we get we could make a corner here that somehow had the correct angle of visibility. Okay, so if you would like to get into this topic and work on something yourself, there's this interesting case of covering with spiral polygons that's still open. So this was a problem that got quite some attention in the 80s, but not so much since then. And it's known to be NP hard to find minimum covers with spiral polygons, but it's not known to be in NP. And I couldn't make the techniques from this new paper and the art gallery paper to work in this case. That was everything I wanted to say. So thank you for your attention.